All right, today we're going to talk about databases. The name of this class is Web Database Integration. In the first 3 weeks of class, we talked about how we're going to be doing web in this course. We're going to be using ASP.NET. We're going to be using Razor Pages. And we talked about how that is set up and how that's structured. And by now, you've done a couple of them. You should be in good shape for understanding how to create them and the basic format of them, the two files that are involved, how the two files relate to each other, and so on. This week, we're going to cover the database part. So we're going to review database terminology and review the normalization rules and review ERDs. I hope all these things are review for you. These should have been in CISS243. But regardless, if this is the first time you're going through this or if it's review for you, since if you haven't been practicing it, sometimes it's hard to remember stuff. So we're going to get you back in the swing, hopefully, with database stuff and database concepts. Databases sort of provide the backbone of an IT world. You can always change the way the data is presented. Like in the old days, you would get printouts of stuff. Now we display data on a web page. The kind of data, though, oftentimes stays the same or relatively changes the same. At the very least, it doesn't change as much as our presentation of it. If we think about an order, what does an order have with it? It has a customer, it has the order date, maybe credit card information, a bill to address, a ship to address, and so on. Then it has a collection of line items associated with it. In other words, you bought such and such item for so many dollars and so on down the line. That one-to-many relationship between line items and orders exists forever, right? From the first time they started processing orders till now, that's the structure of that part of the database. There's a one-to-many relationship between orders and line items. All right. So it stays relatively stable, and what you build on top of the database can vary. So you can maybe you used to display information in a desktop application. You can take that same information and show it in on a web page now. So the presentation of the data changes where the underlying data typically is more constant. I'm not going to say it's constant, but it's more constant. All right, now let's define a few terms here. Make sure we understand them. And I'm going to open up a Word document because my handwriting is atrocious. First key concept is that we want to get is, I don't know why the font matters. Use this one. It's the concepts of data versus information. And just ordinary conversation, as civilians, not as IT professionals, we would likely use data and information synonymously. But in information technology, they distinguish between data and information. And data is the raw facts, whereas information is taking those raw facts and gleaning something useful from them. All right, for example, if I said a company's sales were $100 million last year, That's a piece of data. All right. I'm going to assume it's accurate, but that's a piece of data. Now, is that good news or bad news for the company? Well, it kind of depends, doesn't it? That's not very useful only to know that the organization sold $100 million worth of goods. You know, if it is my t-shirt shop that I run in my garage and I'm the only employee and I print t-shirts on my spare time, if I did $100 million worth of sales, I had a great year, okay? No doubt about it. If, however, we're talking about the Ford Motor Company, for example, if they only had $100 million worth of sales, that wouldn't be very good news. Let's see what the sales for Ford Motor Company is in we're not showing dollar amounts, but we can do the math. Okay, right here. As in 2018, only the F series, the sales generated $41 billion. So if the Ford Motor Company sales was only 100 million, you know, that would be really bad for them. All right. So how can we take data and transform it into information? How can we take a raw fact and change it to something we can use? Well, we can compare. We can compare over time. In other words, what was our sales last year? What was our sales the year before that? And we can see if things are increasing, then the company's probably doing pretty good. If things are decreasing, well, maybe something needs to be looked at. Okay. We could divide and summarize the data broken down, subtotaled in a number of ways. Let's say we're a national company. We could compare our sales in the Eastern region with our sales in the Midwest, with our sales in the South, with our sales in the West region. Let's say we had 4 regions in this company. So we could see, well, maybe the East, West, and South is doing really well as far as their sales. They're matching or exceeding their sales numbers from previous years. Maybe the Midwest region, though, however, is selling less, and that caused a decline in sales. Or maybe they're selling more, and that accounts for the increase in sales. So by subdividing things, by summarizing things, by splitting things up, dividing things, subtotaling things, maybe look at, instead of sales for the year, look for sales by month, and maybe that will. Here's the idea. More ways that we can take this data and transform it to create information, the better information the organization is going to have, and that ought to lead to better decisions. I spelled decisions wrong. You know, if the Midwestern region is dragging down the rest of the company, maybe they need a change in management for that region, for example. If one product sales is doing better than another, maybe they discontinue a product and create a new product to replace it. Any number of different things, but we only get that if we can take that raw information and transform it. And I talked about all the ways that we can transform it. We can organize it, we can sort it, we can break it down, we can summarize it. All those things are things that we can do. And therefore, in the old days, they used to call this field data processing. The newer term for it, newer as in probably the last 30 years, but is information technology. That's putting, the name change isn't just, you know, a name change. You know, it is a meaningful name change. Information technology is a focus on what the system or systems can produce for the organization, as opposed to data processing, which is simply handling the input from an organization. All right. We don't need to just handle the input from the organization. We need to do something with it. We need to transform it into information. And that's the idea of information technology and computer systems. On a very real level, a lot of their job is to take this raw data and transform it into information. All right. That involves gathering data. That involves reporting on the data, displaying the data in multiple different ways, and so on. So in a form that's usable. Information is usable. Data is the raw facts. So I'm not going to go over what came before databases, except to say that databases offer some clear advantages from what came before. In a couple of areas. One of the key acronyms, or one of the first acronyms invented for computer processing, was GIGO, which simply means garbage in, garbage out. In other words, if you put bad data in, you can't possibly get useful information from it. All right. The second truism is the more flexible you can be in taking that data and transforming it into information, the better you're going to be. If I have data in an Excel worksheet, that's my only view of the data, probably. Unless it's a very complicated Excel spreadsheet. So maybe I can see sales by region, but I can't see sales by product, for example. Something like that. Maybe we have a separate spreadsheet for that, or maybe we don't have that particular one. Maybe we don't have sales by region and by product. All right. The more flexible you are in being able to transform, the better off you are, and the more accurate your data is, the better off you are. And relational database systems allow for that, allow for the data to be more accurate and allow for more flexibility. And we'll sort of talk about that. Just keep that in the back of your head. We'll come around to that as we come over, review over some of these other terms and ideas. So that's sort of the whole idea of databases. And I've been talking about databases, and I haven't defined it yet. And probably can find a million different definitions of databases. I would define a database, which is sort of short for relational database, as a collection of related data about entities in an organization. So there's two words in this definition that I want to focus on: entities and related data, because those are very, very important. And that's where we get the true understanding of databases. What is an entity? If we talk about an organization, what is an entity? Well, an entity is largely a noun: person, place, or thing. All right. So if we were doing entities for a college, let's think of what some of the entities would be. There are students, right? Student is a noun. There are professors. Professor is a noun. There is staff. Staff is a noun. There are classrooms. Classrooms is a noun. Are a noun. There is computer equipment. That's a noun. There are schedules, both the professor's schedule and the student schedule. That's a noun. There are courses, those are nouns, and so on. So one of the ways that you identify the entities is you discuss the organization with members of the organization, hopefully of a variety of level of a variety of levels within the organizational chart, and you write down the nouns. All right. But then you think about it a little bit. And you think about what you have, and you try to glean from the narratives that they've given you the entities which exist. Now I'll give you a real simple one, and then I'll tell you of a realistic example. All right. We all know that faculty and professor are roughly synonymous. So if we said, you know, we have 15 faculty members in this division, we have 15 professors in this division, that's roughly saying the same thing. One thing you have to be careful when identifying a problem and discussing it with people is to make sure they don't use the same word or different words for the same thing. So if one person talks about the faculty of an organization and the other talks about the professors of that school, well, it's your job to figure out, yeah, that means the same. Or maybe it doesn't. Maybe one means one thing, one means something else, but you have to figure it out. I'll give you another example that might be a little less obvious. When I worked for a food brokerage software company, the manufacturers of the different food items were either called manufacturers or were called principals. They meant the exact same thing. You know, so Kraft was a manufacturer. It was also a principal for in our database, in the database that we were developing. Now, that's not obvious that those two are the same thing. I mean, we can kind of figure out that professors and faculty are the same thing just because we know, you know, we know the language. But in the case of principals and manufacturers, it may not necessarily be obvious. So you have to do a little bit digging to figure out what those mean and to figure out that, yeah, when one person speaks of a principal, it means the same thing as when another person talks about a manufacturer. At any rate, you get the entities by talking about with the members of the organization, by reviewing documents, by reviewing invoices and purchase orders and all that kind of stuff. Many of you will probably be taking the systems analysis and design course this spring. You'll learn a lot about doing that. All right. So let's say you're happy with the list of entities that you have. We can check that one off of our list. The next part is determining the relationship between the entities. What is the relationship between different entities? All right. Which entities are related? And if so, what is the relationship between entities? When we identify a relationship, one thing that we need to worry about is the cardinality of the relationship. That, simply put, is whether the relationship is one-to-one, one-to-many, many-to-many. So let's imagine we're talking about the relationship between a professor and a section of a course. All right, I've used three nouns: professor, section, and course. So I'm going to represent those as rectangles. Professor, course, section. All right. Now, what is linked to what? All right. Now, one course can have multiple sections. And that's usually represented this way. Sometimes you put numbers alongside of it. There's a good video I have about entity relation diagrams that covers this in more detail. But I like the crow's feet, which this is called notation, because it is the most straightforward in my book. The relationship is said to be one to many. What does that mean? It means that one course can have, doesn't have to have, but can have more than one section. However, a section is only for one course. And if you think about it, that makes sense, right? I'll give you, for instance, CISS243, which many of you probably have already taken. That's a very popular course in our department, and there are many sections of that course. There's online sections, there's in-person sections, all sorts of different kinds of sections for it. I don't know, maybe 10 sections, maybe more this semester. All right, so a course can have multiple sections associated with it if it's a popular enough course. A given section, though, is only for one course. In other words, if you show up to my WebEx room today at 1 p.m. for your section of the course that you're taking, everyone here is for CISS243 section, I think it's B01. All right. So it's not like half of the class is going to be half of the section, or a given course or given section is for two different courses. In other words, half of you, you know, we're not giving credit for CISS243 and CISS268. You know, this section isn't for two different classes. This section is just for one class. So in determining this, you got to go in both directions. One course can have many sections. We already talked about that. A given section, though, can only be for one class. Now, this part gets tricky. All right. You might think that professor and course has a relationship. And this is where, in doing your analysis of a database, you have to look at a bunch of different examples. You can't look at just one. For example, almost all the courses I teach only have one section because they're relatively advanced courses. There's not enough to fill out multiple sections. They typically have one section per course. If you only looked at my courses, you might be tempted to say there's a relationship between professor and courses, whereas one professor can teach many courses and a given course is only taught by one professor. Unfortunately, that's not true in all cases, such as CISS241, where a given course is not taught by just one teacher. A given section is taught by a given professor. Remember, when we see the many, it doesn't mean that there always has to be many. It means that there can be many. So yeah, it's still valid to have this structure even when you're talking about my classes, because I'm the only teacher for this section. If there were more sections, I'd probably teach them 2, but there's only 1. So it's okay if there's only 1 on the many side, as long as there could be many to create a one-to-many relationship. This, by the way, is an ERD. Or should I say the start of an ERD? ERD stands for Entity Relationship Diagram, where we show the entities and the relationships between those entities. Because those are going to be stored in the database. Specifically, they're going to be stored as foreign keys. Now, what if we add students to the mix? You might be tempted to say that there's a many-to-many relationship between students and sections. In fact, you'd be correct. But there's a problem with many-to-many relationships. You can't implement them within a relational database with only the 2 entities. You need to introduce a third entity. So you break this down. Instead of having a many-to-many between 2 entities, you have a third entity, and each of those entities has a one-to-many relationship with it. So we might have, for example, a class roster entity. And a student can have many entries in the class roster. And a section can have many entries in a class roster, because a student could be taking more than one section, and a section could have more than one student. But each class roster record, which matches up the student and the section, each class roster record only matches up with one student and only matches up with one section. So if there's other people in that section, it'd be their student information and the section. If the Zellers took another course, Zellers would be there again, along with the fact that he was in some other course. This is a basic overview of databases. And usually when you're designing, you talk about entities. All right. Some other key terminology. A table roughly is synonymous with entity. So each of these are going to become tables in our database. So it's going to be a professor table, a course table, a section table, a student table, and a class roster table. Each of those entities is going to have attributes. Attributes are characteristics. Professor has a first name, professor has a last name, professor has a certain office that they go to, and so on. Professor has an email address. Students would have similar, their name, first name, last name, phone number, address, email address, and other information about them. Course would have the title of the course, the code for the course. Now, section is interesting because that's going to have a section ID in it. It's also going to have a course ID, and it's going to have a professor ID. Those are known as foreign keys. So the professor ID would be stored in this table to point to the person that is the professor for that course. One thing I forgot to mention is what a key is, a primary key. A primary key is something that uniquely identifies a row or a record in a database, a member of that entity. So for example, each professor here at Loring Community College has a employee number. Okay, each student has a student number. In order to be a primary key to a table, it has to be unique. In other words, there can't be two members of the entity that have the same faculty number, employee number. Two students can't have the same student number. It has to be unique. And also it can't be null for a given student. So you can't have a student in the database if the primary key is student ID that does not have a student ID. So the primary key uniquely identifies members. And a lot of times it's the table name ID because it identifies it uniquely. If we have a given professor ID, we know exactly which professor we're talking about. We can retrieve that data from the database. It's not like, well, it's either this guy or that guy. ID is better than name, right? Because you could have two professors that have the same name, both last name and first name, and even middle initial. Phone number wouldn't be good. What if you had an old-timey married couple that still had a landline at their house and they both had the same phone number? Email, maybe, would be a primary key possibility because no two professors are going to share an email. Does every professor have to have an email? I don't know. It would have to be there, though. It'd have to be there for all professors in order to use it for a primary key. The foreign key is when you have that primary key of another table that points to the table from a related table. All right. So you come up with the entities, you come up with the relationships, you come up with the attributes or columns or fields in each of the tables. Are you done? No. How do you know that you're right? Well, you can show this diagram to the people that you talk to and explain it to them and see if they agree or see if they find something wrong. There's sort of a grammar check, though, and that is known as the normalization process. The normalization process can't assure you that your database is right, but it can certainly assure you if the database is wrong. Does that make sense? In other words, if your database fails the normalization test, it's not correct. If it passes the normalization test, well, that's a good sign, but that's not a guarantee that the database is correct. It's kind of like if you ran grammar check on your term paper and spell check. If it passed those two things, or if it failed those two things, it's probably not a good paper. If it passed those two things, it's still not necessarily a good paper, right? You could have wrote really bad content, and it's a nonsense paper. All right, so I found and I linked to a normalization exercise. And then I've given you an exercise that I want you all to try, and we'll talk about both of those. And then, of course, is your homework assignment. So here's the example. Often what is done in relational databases, and by all means read through this because it's a good reference, is going through a systematic check on the database. One of the key things is eliminating redundant data. Why is redundant data bad? Because it can lead to inconsistencies. And there's a warning here. Normalization is part of a successful database design. Without normalization, database systems can be inaccurate, slow, and inefficient. There's 3 normal forms. And what a normal form is it's they can consider each normal form as a check. You pass first normal form, check, you're okay. You pass second normal form, all right, a little better. Finally, third normal form. If you pass the third normal form, you're probably in good shape. There's a few exceptions that are handled in additional normal forms. But for the sake of this class, we're going to consider the first 3 normal forms. So let's say we had this data. This data has a student that works for NBC Services in London, and they're taking these courses. Intro to PCs, Intro to Windows, Intro to the Internet, Advanced Word, Advanced Excel, and Advanced Access. You can tell this person's in the UK by the cities they chose. This person's another person, has a company, the city, has a list of courses that they've taken. Now, the first normal form says that everything has to have a primary key. In other words, every row in the database has to be identified by one or a combination of fields. And there shouldn't be any repeating fields. You shouldn't have the same data multiple times. And what's an example of the repeating fields? This course name repeats. So this student is taking 1, 2, 3, 4, 5, 6 courses. This one's taking 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 courses. This student, slacker here, has only taken 3 courses. The reason why repeating fields are bad is because you never know how many to allow for. If you had 10 slots for courses, there might be someone that takes an 11th or 12th course. And besides, even if you pick, like let's say you got ridiculous about it and says, I'm going to put 20 courses on there, far more than anyone ever takes. It would make for real inefficient searching to have to look in 20 different spots to determine if a student was enrolled in the Intro to Access class. And plus, you never know when a student would exceed that. So rather than trying to play guessing games on the highest number possible, you want to avoid repeated fields. So what do you do instead? You break that down into 2 tables. A student table and an enrollment table. They call this a taken class table. Where the student is this, we give them a student ID. That's one thing that it didn't have in the original. So student ID of 1, 2, 3, 4. Here's the student's name. Here's their company name. Here's their location. All right. We then have a taken class table, which specifies the enrollment. this combination is unique. So student 1 is in class 1, which is Introduction to PCs. They're also in class 2, class 3, and so on. At this point, oh, I can't write on this. At this point, they're saying there's a one-to-many relationship between student and taking classes. That each enrolled class row only relates to one student, but a student can have many taking classes. Now we could look at this and try to think if there's any problems. We can sort of anticipate some of the problems. Well, one of the problems that might not be obvious here is you could have two people for the same company. And if there's two people working for the same company, that company is going to have one location. And again, imagine this where their headquarters are, not branch offices or whatever. So NBC Services, their company headquarters or worldwide headquarters are in London. There's another student somewhere down the line for NBC Services. It would also be London. That's redundant data. It's repeated data that's not necessary. Likewise, the course name is stored for every student that's taking the course. What if we get one of these wrong? What if the name is spelled wrong for Introduction to PCs in one case? We'd get an inaccurate list of students taking a particular course. So in normalization terms, we look at no repeating, primary key, and that non-primary key attributes are dependent on the whole primary key. So, is the title of the class dependent on the student? No, it isn't. If I take the course, the title of the course stays the same as if you take the course. So this only depends on part of the primary key. So that's a problem. So what do you think we're going to do? We're going to break this out and have student table, a class table, and then a taken class table. What they're taking a long way around to find out is that the relationship between students and courses is many to many. One student can take many courses. Each course can be taken by many students. So they've created this third entity, sometimes called an intersecting entity, that matches up student and courses. So now everything depends on the primary key for each of these tables. Lastly, it looks for what are called transitive dependence. Transitive dependencies. What that means is this. The student determines the company name, but the company determines the location. In other words, NBC Services for Brian is in London. If there was another employee, their world headquarters would still be London. So it doesn't depend on this, it depends on the company. So we would break that down. We'd break that down into two tables. One thing I don't like about that is they don't show the whole thing. So we'd have this table and this table along with these two other tables. And that would be third normal form. Now, There's referential integrity. In other words, a foreign key would be created between company ID here and company ID in the company table. What does that mean? It means I could not possibly put in a database a company other than these companies that are listed here. If I tried to put something that wasn't in here, assuming these are the only 6 companies, the database just wouldn't allow me. It wouldn't allow me no matter what program we used. That's referential integrity. That helps us guarantee that if we put in a company ID, it's one of the valid company IDs. That gives us more accurate data, which gives us, therefore, better information. And I do want to point out in the last couple minutes here, an exercise that I'm asking you to do. You're essentially doing the same thing except with a different starting point. Normalization practice. And again, the expectation is that you actually do these exercises. Remember, this is a blended course. Part of the material is offered online. Part of it is through lectures. So we have this database. And again, it's very common to have data in an Excel spreadsheet and people want to create a database from it. So we have this data in this database, and you were to normalize it. First normalization rule, does it pass that? Second, does it pass that? Third, does it pass that? What I want you to do is go through this and come up with your answer, then watch the video that shows you the author's solution to this problem. And they'll walk you through the process of normalization and make sure that you get the same answer as they do. If you don't, I hope the video explains to you why their answer is correct. If it doesn't explain to you why it's correct, send me an email and send me your answer, and I'll be glad to take a look at it. Your assignment then is to take this description and create an ERD. And there's a video that talks about ERDs. Now, when you create the ERD, make sure you export it into a standard format, PDF or JPEG. Don't give me a Visio file. Your customer will not have Visio on their machine. All right? Therefore, if you create an ERD, you're going to give it in a form that everyone can read, even the non-IT people. But here are the rules that you have to follow. Imagine you had a conversation with the owner of the hair salon, and these were the key points that they had. Design a database that fits these requirements. Now, you don't have to go more than this, right? You don't have to assume that there's multiple salon shops or anything like that. You don't have to do more than this, but you do have to do this. Again, if you have any questions at all, please let me know. All right, that's all I had for this week. Next week, we will start integrating databases onto our web pages. And this is where the fun really starts. So if there are no questions, that's all I had for today. We'll either see you in lab or we'll see you next week.